Morning. Let's work on this question. All right, this is the question about motion and it's slightly different than what we had before because it involved knowing the acceleration, try to find velocity, and then knowing the velocity, we'll try to find the position. The question is, we find its position at a time equal to 1. So in order to find the position, we have to know the position function. It's kind of a process here. So it involves two of the integration process. We have to find the velocity and find the position function.
Yes.
So we already have the acceleration function. According to what we know, acceleration function is the derivative of the velocity function. So from here, we can start calculating the velocity function, which is done by integration. So we have at is a derivative. So since we have at, the t, we have a prime of t, so at can be calculated using integration. So at is the integral of the at. So we have to integrate acceleration function, and this is a vector form. So let me try to write it into. So we're integrating. There's a vector t. At is t1, and then t. To integrate from there. This is our calculation for Vt. We're going to integrate them one by one. So for example, the first one is t. If you integrate t is t squared over 2. That's the antiderivative of t. And then we calculate the second component. We integrate 1, integration of 1. The antiderivative, one of the antiderivative is t. It's the second component. The third component is also t. So we will get that one,
Yeah, basically just t squared divided by 2.
right? Okay, so that's the antiderivative part, but then also there are initial value because we were doing a indefinite integral. So there's a plus c. That comes at the initial value. You see, in this function that we're calculating, if the t equals 0, for example, if t equals 0, then these are all 0. That's all 0. So that means the c has to be the actual value for v0. Since we have the v0 over here, it's actually vector 1, 1, -1. So 1, 1, -1. So that has to be the c there. So then we now have the vt function. Vt is equal to this entire function added with initial value. So we finish determining the vt. But that's the position function. To find out the position function, we have to do another integral. We know that the velocity function is a derivative of the position function. So according to what we know, vt is equal to the derivative of rt. And the position function is normally we denoted as rt. So determine the position function, we have to do a integration. So rt equal to the integral of vt. Vt is a derivative of rt. So rt is the integration of vt. And that's the reason now we have to answer this question by integration. So what we do, we are integrating the vt. The vt we just find out, and let's try to write that vt into a vector form. The first component, let me just write it, type and write at the same time. Exactly. So the first component is t squared over 2 plus 1. The second component is this t plus this one is t plus 1. Last component is t squared over 2 minus 1. So it's t squared over 2 minus 1. Right? And we're going to integrate this for the position function. So let's look at the integration. This is equal to, you can still see it. It's in space. Let's finish the integration. Remember the initial condition. Okay, it says it starts with the origin. A particle start as the origin, which means the initial condition is 0, 0. So we don't have to worry about that. So finish integrating, and then the c should all be 0. And then once you find the initial position, you're going to determine the position at t. So I'll let you finish integrating this. Once you finish integrating this, you make t equal to 1. That should be your final answer. So you guys finish the rest of the calculation on your own. This is not. Then rest should be able to finish the calculation. I mean, whenever I try to do it with you, I think I probably did a lot more lengthy version of it than was it. Andrea, you double check. see, do you need to stay on this page? Is it okay? Because this is the page where you can see your submission. So if your answer did not get submitted, you should. So the idea would be, we know we already have the acceleration function. It's the derivative of the velocity. So we would integrate the acceleration function to get the velocity. We then know the velocity is the derivative of the position function. So we integrate the velocity function to get the position function. So that's really the underlying reasoning for what we calculate. And then of course there are little detail. I try to avoid making calculations, right? So, but we want to double check to make any calculation mistakes. Check what's the word. If I have any typo, you can also let me know. You look at my process, right? But sometimes I also have typo or calculation errors. If you can't see one, you feel free to mention that. So it's the record writing. If you haven't finished it, I only have 15 answers so far. So the calculation, integrate t squared, we have t to the power 3 over 3. There's already 2, a 3 and a 2.
Oh, yeah, I'll multiply the 2 by 6.
Right, yes. Right, so that'll be the first component and then plus t. Then again, you make t equal 1. And then this you integrate into t squared over 2. That's integrating the t and then integrating the 1, we have t. And then the term after that is going to be t to the power 3 over 6 minus t. So that will be the position function. The initial position is at origin, so we don't have to add, or you can see we're adding a 0 factor here. It's the initial position, it's at 0. And then you make, that's right, thank you. Make t equal to 1 in the final calculation. That will be 1 over 6 plus 1. That would make it 7 over 6, and then 1 over 2 plus 1, that will make it 3 over 2. 1 over 6 minus 1, that will make it negative 5 over 6. No.
Yeah.
Equal to 1. Let's go back to that page. And this is all I have recorded. All your answer has been submitted. So 19, about 19. Mission. Final answer should be D. The calculation. Do you have any homework question you want to ask before we start section 4? Chapter 11. Any question? Any homework question? We're doing all okay with motion? Have you finished your section 3 homework yet? Are we doing okay? Right. If you guys have no questions so far, let's go forward in chapter 11. So we're learning Baxter value function and being applied to using calculus to study the curve represented by Baxter value function. Baxter value function can also represent motion, so we can use it as a model to study motion. Now, here we're going to move in a little bit further in chapter 11. So we're talking more about motion using Baxter value function to represent motion. So here the title is called Unit Tangent and Normal Vectors. Actually, there's this unit tangent vectors and there's unit normal vectors. These are the two we want to talk about the curve, a curve that we're using Baxter value function to represent. So now with the vector value function, we're capable of representing three-dimensional curve that is going around in space. So let's try to, well, this is how the textbook is handling things. Instead of explaining the reasoning behind it, we actually go ahead and start with the definition. And this is a term define the direction of the curve. I mentioned that tangent vector or tangent function. The tangent vector is the derivative vector. Basically, if you have a position function representing the motion of any object, then the derivative of the position function will represent the direction of the curve at any given moment, at any time. But that direction, which is the r prime vector contains two things. Number one, it contains the speed. The magnitude of the derivative function is how fast the particle is moving, and also contain the direction. So now this is a definition that separates the direction from the magnitude. The unit tangent vector is to turn the r prime vector into a unit vector, and that is what we call a unit tangent vector. Okay, so r prime is already the tangent vector, but it's not unit vector. Sometimes r prime can be smaller than one in magnitude, and sometimes r prime is longer, which means has a bigger magnitude. That means the particle is moving really, really fast. So now we are turning off the magnitude of r prime, extreme of the speed, only worry about angle. So that's where things are going. Are we going straight? Are we turning left or turning right? Okay, so this is the angle information here. Now, if the RT is a two-dimensional vector, then the tangent vector T, the T vector, would be a unit vector in two dimensions, like cosine theta, sine theta. So you can directly identify the angle of the motion. Okay, so here's a little exercise on working out the unit vector. And then you can see what's this carrier. It has the benefit of showing the actual direction of where everything of the curve is going, but also have this burden that we're dividing the r prime with r magnitude of r prime. Whenever we have a division, then division add complexity to the function representation itself. That means that the form that we are looking at would be a little bit complicated. So here's a little exercise on the calculation of the unit tangent vectors. Here we go. I'm going to try to practice solving it. But calculation of it, by definition, tangent vector, unit tangent vector is a vector defined by it's r prime t, the derivative vector, divided by the magnitude of the derivative vector. Okay, so it's not too complicated, but then the first thing is we gotta have r prime to begin with. So we have r, and then r prime is equal to the derivative of cosine t is negative sine, so it's negative 3 sine t. And then derivative of 3 sine t is 3 cosine t. Derivative of 4 t is 4. So that's the r prime. And because we need to turn it into a unit vector, we're gonna find the magnitude of this. Magnitude of r prime. I skip the letter t. It's supposed to be magnitude r prime t, but I'm writing it. So 3 squared is 9, so it's 9 sine squared t plus 9 cosine squared t. And then plus 4 squared is 16. Now sine, 9 sine, 9 cosine is actually 9 sine squared t plus cosine squared t. We find the common factor between the two terms and realize we have sine squared plus cosine squared, that is equal to 1. So this is essentially 9 plus 16. Plus 16 is 25, so this is equal to 25. Which is equal to 5. So it's nice that the denominator is not A fraction is actually a integer number. So now we can finish our definition, finish the calculation. So the definition, we now have our tangent vector, which is equal to every component in R prime have to be divided by 5. So it's -3/5 sine t. And 3/5 cosine t. And then lastly, 4/5, every component divided by 5. That's the first part, it's finding the tangent vector. And then we were supposed to calculate the tangent vector's value at 0 and at 1. So if you make t equal to 0, it's t prime, t vector at 0. And t equal to 0, sine 0 is 0, so that's 0. And cosine 0 equal to 1, so that's 3/5. And that's 4/5. So you can see the magnitude of the prime at t0 is 1. And the other question is to calculate t1, the tangent vectors at t1. With t equal to 1, I have no other way, I'll just write it. 3/5, it's sine 1, reading measure sine 1, and 3/5, sine 1, and then 4/5. It's pretty much it is with us to answer those. So I finished calculating everything in this example. It's exercise on determining and applying the unit tangent vector. Any question? Okay. So our first example. Let's see how tangent vector can be applied. Now it's the answer to the question. You can compare with what we had. That is a graph of both vectors. You can see that the red arrow in the picture, these are the unit tangent vector at 0 and at 1. Let's see, they're all pretty short because magnitude equal to 1. That means the length of the arrow equal to 1. It's magnitude vector. Moving on, this was another question. This is a two-dimensional example. This one, hopefully, we're able to graph it easily because two-dimensional graph are always harder. Two-dimensional graph are slightly easier. This is the same question that we had earlier in second section, 11.2. We have a parabola that was 45 degree. So we got a parabola that's slanted pointing to 45 degree. And we want to find the unit tangent vector for this function, and we want to calculate t0 and t1. So we're doing the same exercise for this function. The calculation for the unit tangent vector process will be, first you have to find the derivative. Derivative of t squared minus 1. T squared minus t is 2t minus 1. Derivative of t squared plus 1 is 2t plus 1. Okay, after finding the derivative, we have to find the magnitude because we are going to take r prime divided by magnitude r prime. The magnitude is the first component squared plus the second component squared. We're able to cancel the degree 1 term. We end up having only the degree 2 term and a number. So that's our prime. And then we're going to do a division to get the vector t. And that's combining the division with each component. Each component is divided by its own magnitude. So with that vector, you can make t equal to 0 to get a 45 degree angle. If you can see, t0 is negative. It's 45 degrees this way. And then the t1 is when t equal to 1. And we have an angle. That's how the special angle is 1/√10 and 3/√10. It's not like we know. Any question? That's this example. Two-dimensional example. The angle can also be graphed on two-dimensional plane. The picture. You can see that this is t0 right at the origin, drawn at the origin. This is a t1. That's when t equal to 1. 1 is at 0.2. 0.2 is the x value and y value, but t is equal to 1 there. these are two examples on calculating the unit tangent vector. And let's moving on. So we're going to define something else. It's called unit normal vector. I hope that now we can start connecting the word normal with perpendicular relation. When we are talking about plane, we have normal vector for plane, which is vector perpendicular to the plane itself. Now here we're going to talk about vector to the curve. So unit normal vector is a vector perpendicular to the tangent vector. And then so therefore the unit tangent vector and unit normal vector, they're perpendicular to itself. And you should draw at the point of tangency. One is following the direction of the curve. We're moving this way. Okay, so this is in the same direction as the curve itself. Now the unit normal vector is perpendicular to it. We often, in physics, we often try to decompose the vector to the part that's in the same direction as the motion, the part that's perpendicular to the motion. Because so our understanding is when the force are perpendicular to where the motion is, this force does not affect the motion itself. So for example, if you are in a train that's moving forward, then pushing the force that go in this direction or this direction, like along the travel, the motion or against the motion, those forces affecting, like slowing down the motion or speed up the motion. Those forces are either with the motion itself in the tangent direction. But if it's perpendicular to the motion, perpendicular to the path itself, that kind of force do not have impact on the original velocity. So we kind of want to different. So that's the reason why we often want to decompose any other motion to which part is perpendicular, which part is along the curve. So tangent direction, direction. Okay, so how we calculate it? The definition for the normal vector is since it is perpendicular to the tangent vector, in order to be perpendicular, we get the idea from previous session that if you have a function that has a constant magnitude, then the derivative of that function will be perpendicular to the origin. Remember the unit vector, the RT, when it has when it's a unit vector, then the derivative of RT will be perpendicular to RT itself. So therefore, our tangent vector, the one we just defined, the T tangent vector, TT, okay, magnitude of tangent vector equal 1 because it's a unit vector. Therefore, we naturally have this consequence that T prime, the derivative of T function will be perpendicular to T itself. So that's why we do T prime, we find derivative of the T function, the derivative of T prime, which will be perpendicular to T. So now that satisfies the perpendicular relation. And then we want to find the magnitude of that vector. Therefore, now we're making it into a unit vector as well. So this is our definition for unit normal vector. And the reason that we define it this way is just to guarantee it's perpendicular. Now, this definition is conceptually easy to understand. So the division will make sure this is a unit vector. Now the T prime, the prime action is to take advantage that T vector itself is a unit vector. Therefore, T prime is naturally perpendicular to T. So that would be the reason for the definition. But there's a little problem to this definition. That's a complication calculation. Now, T vector itself are often defined using division in the first place because T as a tangent vector is a division of the R prime and magnitude R prime. So when the T function itself has division, then derivative of the division, remember, you have to quotient rule. So we have to expect some level of difficulty, which is the reason that sometimes we try to find other ways to find the normal vectors value, because we know this definition can be hard to do. Right here, we first would follow the definition. So when we see a hard question, we might try to turn around, figure out some alternative way for the computation. So here we have a function RT, and the question again is to try to find the T vector, and find the derivative T vector to find the normal vector. And we're going to sketch the t pi over 2 and n pi over 2 because these two are supposed to be perpendicular. And so that would be the idea. Let's see. The good thing is this function we have already did it in the previous example. So maybe that will save us some time on the computation. So let's see. Same example. So we have sketch. So the same function. So let's calculate the we have it already here. Continue. So now we already have the tangent vector, so let's do the normal vector. This will be the derivative. So let's see, normal vector notation is n vector nt. So by definition, it should be the derivative, the tangent vector divided by the magnitude of the tangent vector's derivative. So what we're going to do first, we want to find the derivative. And the good thing is tangent vector is if we were able to handle the division, the vector is a constant magnitude of 5. So everything divided by 5 is not too hard to find the derivative. T prime is derivative t. So then we find derivative sign is cosine, so that's negative 0/5 cosine t. And then the derivative cosine is negative sine, so it's negative 0/5 sine t. And then derivative of the 4/5 is 0. There. And then let's find the magnitude of t prime. So the good thing is it's cosine and sine. So you square this, you have 3 squares 9/25 cosine squared t plus 9/25 sine squared t. We square the same. And then we square the last one is actually 0. So 0. So factor of the 9/5 is cosine squared plus sine squared plus sine squared equal to 1. So 9/25 squared root is 3/5. So we have a magnitude of 3/5. That means that every component here you divide it by 3/5. So now we have that was definition. So follow the definition. This is equal to every component in the t prime is divided by 3/5. So the coefficient 3/5 is now divided out. To divide out, we have a component that goes negative cosine t and negative sine t and 0. The question is to draw to sketch t pi over 2 and n pi over 2. We're trying to illustrate the chemical relation. So t pi over 2 at 90 degree, t pi over 2. This is the t. If t is pi over 2, sine pi over 2 equals 1. So that equals negative 3/5. Since sine equals 1. Cosine pi over 2 equals 0, so the middle is 0. And then we have 4/5. Right, and then n pi over 2. The angle is pi over 2. Then let's say cosine pi over 2 equals 0. So this component is 0. Sine pi over 2 equals 1. That's negative 1. Last one is 0. So you can clearly see that the dot product between the two is definitely 0 because they were perpendicular. So negative, that was 3. It's negative 3/5 times 0 plus 0 times negative 1 plus 4/5 times 0. So the dot product equals 0, and they are perpendicular. The graphing part will difficult. That's the graphing part, and it's pi over 2. To graph the two-dimensional factors. so. X, Y. And B. Whereas these two are okay, but you have to, these are vectors, you have to have initial point. The initial point of the vector should be on the original curve. So it's not just graphing these two vectors. It's graphing these two vector on top of the original curve. So we have to graph the original curve. The original curve is a spiral motion. It starts with t equal to 0. T equal to 0, it's 3. The initial point is 3, 0, 3, 0, 0. It's on the x-axis. So start from here. Okay, and then when the pi over 2, cosine pi over 2 equals 0. So at pi over 2, we have cosine pi over 0, 3, 0, 3, pi over 2 times 4. Times that's 2 pi. So the z value is 2 pi. So so you have x equal to 0, y equals 3, and b is the height. The spiral motion. So we were supposed to graph it right here, and then this and the normal vector is 0, -1, 0. So it's an angle that's -1 in the y direction. Like, so it's opposite to the y-axis parallel. And then 0 in the z direction and 0 in the x direction. So it's pointing that way. That's a normal vector. On the other hand, we were supposed to draw this vector, the tangent vector. You can see how the curve goes. So it's going -3/5 degree, 3/5 unit in the x direction, 0 in the y direction, and then 4/5 in the b direction. So a better version of the picture, just want to say that the difficulty in the graphic is how can we graph the spiral. That's why I hesitated when I'm trying to graph it. I can only roughly sketch it. When I'm trying to sketch it, my sketch is not very realistic. All right, moving on. There are other questions are determining the normal vector, sketch RT with the normal vector at T. I'm just skip that question. Basically, we follow what we had earlier. We have already calculated the tangent vector T, but it's the division, right? So with a normal vector, I have to find the derivative the quotient. So we know we have to do either quotient rule, product rule, if we want to calculate the NT by itself. Here is the process. It's a really lengthy presentation, but if want to try to draw it myself, I know how long that's going to be the way I write large. The tangent vector, we have already done it in the previous example. Now it's a question about trying to find derivative. So this differentiation, what we have on the board is quotient rule. So according to quotient rule, the denominator has to be squared. Numerator, you will find derivative of the numerator, which is 2 multiplied by the denominator minus the numerator multiplied by the derivative of the denominator. That was doing that's through chain rule and power rule. And then we have to combine the terms and figure out a way to simplify it. And that's the part that gets lengthy. Some of the terms can be combined together. We have to move that -1/2 power down to the denominator to get the denominator of 3/2 power. And the both first component and second component have similar format. So you kind of compare and then simplify them. They have very similar form. And then we can find the magnitude of this vector. And so the division, we find the magnitude and divide the original derivative with the magnitude. We end up having the normal vector. This is a really lengthy process. But the whole point of this is to get to one thing. You can see the normal vector and you can see the original t vector. And we have a funny, interesting relation. The t vector, the tangent vector is 2t minus 1 over the magnitude of the derivative, and then 2t plus 1 over the magnitude of the original derivative. And then here we have the normal vector. It is 2t plus 1 over the magnitude, and then negative 2t minus 1 over the magnitude of the derivative. So we have very interesting relation. The top formula is a unit tangent vector. In this page, the bottom formula is a unit normal vector. So it looks like the x and y are being switched. Do you notice that? So they have that. So for two-dimensional normal vector and unit tangent vector, they have that relation. They have that relation. The reason for that is because these are considered cosine theta and sine theta. What is perpendicular to the cosine theta and sine theta is this. Actually, so that we can learn a few things from it, even though I don't want to dive into this lot of complicated calculation there. So if you have a unit vector in 2 dimensions, this unit vector will have a magnitude equal to 1. And here is our theta. So then the x value on this vector, at this point, the cosine theta is going to be the x value, and then sine theta is going to be the y value. Suppose this is our unit tangent vector, then unit normal vector is supposed to be perpendicular to it. So it goes like this. To make it perpendicular, easy, what happened is like this theta is the perpendicular relation. So this theta becomes that theta. And therefore, what happened, this is going to be your x value. It's going to be the cosine theta. And then your y value is going to be the sine theta. So in the normal vector, what happened, see the lengths are match. This part is saying that this part, there's a similar triangle going on there. So for the normal vector, you can use the sine theta. The sine theta over here becomes the negative sine theta over here, and then cosine theta. So you switch the x and y this way. Or it could be, as far as perpendicular direction, you can have the normal vector in this direction. In that case, that this is now the theta. Try to make sure that we draw the perpendicular relation. So that one would be the sine theta. So this will be positive sine theta and negative cosine theta for the y value. Assuming these two are positive. Right? So what happened is your normal vector could be negative sine cosine. You switch x and y, make one of them negative. Switch x and make one of them. This is switch x and y, make the x negative. This is switch x and y, the x and y switch, and then the y become negative. One way or the other, these two normal vector I'm drawing, they're both perpendicular to that tangent vector. So in 2 dimensions, whenever you try to identify the perpendicular vector that is the unit vector, you have that effect. So it looks like we could go from here directly to the normal vector without going through the lengthy calculation. So those are the illustration of those vectors. Now let's try to summarize this. Suppose RT is a 2-dimensional position function, and T function is the T prime. T prime is smooth on the open interval, assuming that you actually have a derivative that doesn't have any sharp corner. In that case, that we're able to find the magnitude of T prime. So we see that sentence T prime is smooth, because if T prime is not smooth, then T prime equal to 0 vector. And remember, we have to divide the magnitude of T prime. If T prime is a 0 vector, the magnitude of T prime equal to 0, the normal vector is undefined, which makes sense. If the vector have any sharp corner, of course, we're not able to find the tangent vector. We also cannot find the normal vector either. So only smooth curve has proper derivative, therefore has proper direction, and therefore has those tangent vector or normal vector. All right, then the normal vector n0 is either negative T2, T1, or T2, negative T1. Now it's assuming that T prime is, the T vector is T1, T2. So we're saying between the T vector and the N vector, we have that, like switch that relation. You can switch the X and Y. T1, T2 is the X and Y for the tangent vector. Then the normal vector equal to switch T1, T2 at negative, or switch T1, T2 at negative there. It doesn't matter which way do it because it could be the positive 90 degree from the tangent vector or negative 90 degree from the tangent vector. That was a positive 90 degree and this is a negative 90 degree, but it's 90 degree with a T vector anyway. Because you can do that, you can multiply T1, T2 times if you make T2 put on negative T1. They're perpendicular. For the vector to be perpendicular to itself, the unit, the dot product equals 0. So both this N vector and that T vector, the dot product equal to 0, which guarantee that they're perpendicular. Any question? So we're trying to summarize what we observed in the previous example to give us a shorthand of the calculation of the normal vector. So maybe knowing the T vector, you already have the N vector, so we don't have to go through all those lengthy process. Let's find the derivative of the T vector. Let's find the magnitude of T vector. Let's divide them to get the normal vector. So those processes sometimes can be complicated. So if it's two-dimensional, then the normal vector and N vector can be, they go hand in hand. All right, last sentence saying whichever the vector that points to the concave side of the graph are. So that is, even though we have two choice of N, which one it is depend on the direction of the curve. So that is what we're trying to talk about is this. Which one is it? Should be this one, which is like a negative T2, T1, or this one, that's the T negative T1, negative T2. Which one is it? Which vector makes more sense? The answer is whichever is a concavity. So if you get a curve that goes this way, and then this is your normal vector, and this is your concave point, so that has to be your normal vector, so a T vector. Now, on the other hand, if your curve goes this way, then this is your tangent vector, and that is your normal vector. So your normal vector is supposed to be perpendicular to the tangent vector and also pointing to the center of the concavity. Any question? So which way are we? There's two perpendicular vector, this N and that N. Which one it is, it depends on the actual curve itself. That's why that last sentence saying depend on the concavity. Our vector. So now let's talk about component of the acceleration. So basically we're saying when something is moving and the derivative of the velocity function is called the acceleration function. Acceleration often affected by force. So depending on like which way are the engine is moving us to. So we want to decide which component of the force is making us going forward, which component of the force is actually trying to turn things around. Okay, so we can decompose AT into this. AT is equal to AT. This is a decomposing AT into the one that's in the T direction and the one that's in the N direction. So this is, AT is a vector, so it could have a decomposition. And you can think of it as projecting AT onto the direction of the tangent vector. And therefore the rest of them will be perpendicular to the tangent vector. We've done this kind of thing before when we project one vector onto another vector. But here we just want to try to do it more semantically. Now, this a little t, a lowercase capital, a capital T and a capital N, those are the magnitude of the acceleration in that direction. So here we're further decomposing them. The magnitude are separated from the direction. So T prime, the T vector and the N vector, these are all unit vectors. So it doesn't contain it has angle relation. It doesn't have any magnitude, the strength of the acceleration in that direction. These are all in those absolute value there. So this is what we call a component of the acceleration, either in the parallel direction to the direction where the curve is moving, and the other one is perpendicular to direction. In a way, we think of the acceleration in a way that these two components, because these two components have different effects. The AT in the t direction will make things move, increase the speed. So this one is like moving in the same direction where the curve is going. Now the AN there is not going to increase the speed. Instead, it's going to turn things around. Whichever that direction is, it's changing the direction that things are going. So one is increasing the speed, one is affecting the direction of the motion. Are we okay? So we are separating the acceleration into two parts. One is causing things to go fast, only affecting the speed. That's this one. And then one is like only going, if it's this way, like the curve is going that, it's going to go further. It's making things turn. So that's one that's turning. So this one does not affect the speed at all. And then this one is affecting the speed, the other one only affecting the direction. So we're separating the two in the acceleration. So this, we can clearly tell which part is causing the direction to change, which part is causing the speed to change. Any question? All right, so let's do the decomposing part. So how are we exactly do it? Okay. These kind of explain all the stuff I was talking about, and then let's look at how do we do it. If we multiply both sides of both sides of this equation by the vector t. Okay, so these are the calculation. This vector at can be calculated by multiply both sides of the equation. Think of this equation taking this as given. So given this at decomposition, you can multiply both sides of this by t vector. Remember, t vector is a unit vector. If you multiply both sides with t, and t, then t times the n, t vector and n vector is perpendicular. That will be 0, right? That will become 0. And then over here, then t vector multiplied by t vector is, dot product to both sides of the equation. T dot t is 1 because it's a unit vector. That will be the at. This will be 0. And here it's going to be at dot t vector, right? So that's why we have this formula. Down here we have the formula saying that component, that number is the absolute value. It's a number. So that's why it's a dot product. So at equal to a dot t. So that's our tangent vector. This is our acceleration. Therefore, that's the second derivative. Remember, the tangent vector is the first derivative divided by the magnitude of the first derivative, right? So we can actually calculate at at the bottom left. Are we okay? We have 10 questions. Now with that one given, and then that's moving on to an. So how do we calculate an? Again, you take this one, suppose we have it, then you dot nt on both sides equation. This is a second derivative of the motion function multiplied by the normal vector. And that will be this. And then the t dot n will be 0 because perpendicular. And n dot n will equal to 1, and that's an. So an equal to a vector, acceleration vector multiplied by the unit normal vector. So the bottom line is the way, if we are able to decompose it, here are the formula for an and at. Those are the magnitude in either direction. So those are the two, the coefficient of the vector or the magnitude of the vector in that direction. These two are the direction perpendicular to each other. Any question? So sometimes we want to know those numbers. We want to know how much the AT is in this direction or that in the T direction or N direction, because we wish to find out how much is our speed getting smaller or bigger. And if the AT is positive, of course, speed is getting faster and faster. If AN is positive, that means the direction is changing. So, and then that also means if A equals 0, we're going in the same direction. And then if AT equals 0, that means we're changing direction without changing the speed. So it will give us some idea of how the motion is being affected. So here, a summary, and this is really the part that will give us a way to calculate those components. So how do we decompose the acceleration function into these two separate directions? Down here we have AT equal to acceleration function multiplied by the unit tangent vector, which also equal to the derivative of the speed, magnitude of velocity is speed, derivative of speed. Because after all, AT represent how fast the speed is changing, right? This part is only of the ATT changing the speed, ANN changing the direction. Now, AN can be calculated by, originally in the previous page, we have AT dot NT. Okay, this calculation can also be calculated as the square root of A, magnitude of A squared minus AT, because AT, AN, and N, they form a right triangle. So this AT, magnitude of AT is a hypotenuse of the right triangle. If you already have AT, it's like having the short leg of the rectangle and having the hypotenuse. And then AN is really the other short leg of the right triangle. So we can do a Pythagorean theorem if AT has already been solved. There are two more formula for the computation. The reason that we have so many formulas is because sometimes we want to know one over the other, and the direct calculation can be complicated. So we have some alternative way for the calculation. Any question? Okay. Let's try to explain all the other one. This is AT cross VT. The reason that will work because AT cross AT, the magnitude of the cross product represent the area of the parallelogram. So then area of the parallelogram divided by one side of the parallelogram, which represent the height. So we can think of it from the perspective of geometry. And any question? I find the other two little easier for calculation, especially this one for as far as calculating the AN. That's why there are 4 different formula for calculating AN, the normal directions of accelerations magnitude. Any question? So we're going to see how these formula can be applied when we are solving a problem. Okay, so this is the same question that we had earlier. This question is actually not too hard. We're just using it to illustrate and make a point. We have already determined the tangent vector and the normal vector. We know these are perpendicular. And if we want to calculate AT, what we did is take the tangent vector and dot the acceleration function. So using the dot product, we are able to determine how much of the acceleration is in the tangent vector. It's like along the tangent vector direction. We end up having a 0. So that indicating that there's a constant speed. This is a spiral motion. In a spiral motion, things are moving always with the same speed. It's the same spiral motion. So it's understandable that in the acceleration, there is 0 change to the speed, AT equal to 0. All right, next one you can see AN is calculated by AT acceleration function multiplied by the normal vector. And that's our normal vector. And this is our acceleration function. It's the second derivative of the motion. You dot these two, right? And you can tell that the value of the dot product equals 3. So that is how much the acceleration is affecting the direction. And then that basically indicating we have a constant change to the direction. So every moment the spiral is changing its direction. Always, actually it's the same amount of change. any question. That's why it's going in a circle, right? It's always changing the same thing. That was the example showing that it does put some more understanding on which component is changing the speed, which component is changing the direction. All right, we're gonna do the same. This is the question that we had the parabola. So with this parabola, we find this tangent vector. We'll also find this normal vector. Now we want to see how much of it is changing the direction, how much of it is changing speed. This parabola, the motion, I believe it changes direction, also changes speed. And we can tell. So we're going to try to multiply it. And first we'll have to find the second derivative. The first derivative, 2t minus 1, 2t plus 1. So second derivative will be 2, 2. So we have a constant second derivative. We're going to take the second derivative, multiply AT and AT, dot product, dot plus AT and NT. So AT dot T will give us a component in the how much is changing the speed. You can see AT dot T, basically 2 times the first component, 2 times the second component, and some of the factor are changed. So you can see this is how much change happening to the speed. It's affected by the T. When T equal to 0, we see that this change component becomes 0. So when T equal to negative, it will have negative impact on the speed. Acceleration changes the speed. So at first, T equal to -2, -1, so the speed gets smaller because acceleration is making it smaller. And then after T equal to 0, when T become positive, we have a positive AT. That's when the speed gets faster and faster. So we can tell from that. AN is really calculated using a different approach, but you can also do AT dot NT. I think we will get the same answer with the dot product. It's 4 over the magnitude of the first derivative. And we can see that for larger T, the direction is changes very small because of the denominator. When the T is large, this change to the direction small. Whenever the T gets smaller and smaller, it drastically changing the direction. That's why, right? At first, there's slight change to the direction, and then it suddenly change at 0, and it gets slight change again. So even the direction change are affected by the T value. And it shows in the value of AN. Okay, so the last example was about projectile motion. I think it's a similar approach, but we can kind of borrow some idea how to calculate AT and how to calculate AN. Let's look at a couple examples from our own homework to see if we're able to figure out the answer or if there's any difficulty in the calculation. I didn't find a lot of questions in this category, so there's only 4 problems, but it has its own value. And this was a calculation of the tangent vector. So you find the first derivatives, for example, derivative of the x component is 2, and then we have -2, then we have 2 again. Okay, so every component has to be divided by the magnitude. Let's see what is a tangent vector, unit tangent vector. So 2 has to be divided by the magnitude of 2 squared, 2 squared, 2 squared. 4, 4, 4, right? 12. So divided by the square root of 12. Magnitude 2 square root of summation of square, and then it will be the same, -2 over square root of 12. And this last component is 2 over square root of 12. I believe that will be the tangent vector. It's all because that the derivative is constant, so we won't have too much difficulty by tangent vector. So that was the first example of finding the unit tangent vector, just learning the derivative vector into unit vector. This one I think is the same. You find the derivative and you divide it by magnitude. So try it yourself, and we're going to try to move on to one lecture. Oh, this one. This is exactly the same one as our question, except you have to apply chain rule. So the derivative is slightly more complicated than what we have in our example. So let's try. Sure. The question on calculating the tangent component and normal component of the acceleration. So the magnitude of the acceleration for either component. Because it is a spiral, so we shouldn't have too much difficulty in determining its derivative and the tangent vector. So we have r prime, which is the derivative of cosine 3t. Derivative of cosine is sine, negative sine, so it's -3. It should type it. -3 sine 3t. We have to do a chain rule. So and then the next component is derivative of sine 3t. Derivative of sine is cosine. So there's a chain rule. We have to do 3 cosine 3t. The second component, the last component is 6t. The root of 6t is 6. So now let's find the magnitude. The magnitude of this is square root of 3 square is 9, so we have 9 sine square. 9 sine square 3t plus 9 cosine square 3t. And then the last component is 6. Square of 6 is 36. Right, 9 is common factor. Then you have sine square plus cosine square. Cosine square plus sine square equal to 1, so that's 9 plus 36. So this magnitude is actually square root of 35. There. So then the tangent vector is t equal to -3 over root of 45. Root of 45, maybe we can simplify this. Root of 45 is 5 times 9, which equal to 3 root of 5. So -3 divided by 3 root 5, which is really 1 over 5. It should go here and simplify. So I just want to make the division a little easier. So it's 1 over root of 5. So here, so sine 3t. And then there's 1 over root of 5 cosine 3t. Then we have 6 over 3 over 5. 6 cancels out 3, which is 2 over root of 5. That's the tangent vector. I want to follow what we have in our definition. We can find the derivative of this to find the normal vector. Well, we can do it faster. We can find the second derivative, which also would be the AT equal to the derivative r prime, which is -9 cosine 3t. Okay, 3 cosine derivative of negative sine, so it's -9 sine 3t. And derivative of 6 equal to 0. So there we have it. That's the AT, and then right here we go back to the calculation. AT equal to vector AT dot t. That's right. It's equal to acceleration function AT. That's the one that we find out. Essentially, we need to take this vector dot this vector. So it's the dot product between these two, right? It's our definition. So this is supposed to be equal to a vector dot t vector. So dot product. Dot product calculation is different than the cross product calculation. On the exam, I had people accidentally do the cross product calculation when they were supposed to do a dot product calculation. So these two multiplied and these two multiply, the last component is equal to 0, we don't have to multiply. So if we multiply these is positive 9/5 sine times cosine. These two is negative 9/5 sine times cosine. So essentially it's 0 then, right? 0. So which kind of makes sense. Remember, if I have a spiral, for a spiral, the tangent AT vector is in the tangent component, right? Spiral, the tangent component is what's changing the speed. For a spiral, the speed does not change at all, so that part is 0. And then we have the AT. But then since AT equals 0, we can understand the AN is all the magnitude. Go back over here for the decomposition there. Now it turns out the A and AT equal to 0, so this part equal to 0, that for A vector equal to AN times the unit vector NT. So then the AN is the magnitude of the acceleration, right? So that will be it, because that one was 0. This one is all we have. That's really the magnitude of the acceleration multiplied by the unit vector of the acceleration. So AN essentially is the magnitude of the acceleration function. So because that one is 0, this is basically the magnitude of the AT that we have now. Right, so we already have this. You find the magnitude, you have 9 squared, which is 81, plus cosine squared, plus 81, and sine squared, and then take square root, and that would essentially be a 9. So the magnitude of the acceleration equal to 9. So the last question we go, which is really 9. That's really the magnitude of the acceleration. So it sounds like a very complicated question, but when you sit down and look at it, it's really looking at how much component of the acceleration is in the tangent direction, how much component is in the normal vector, is in the changing the direction. So as far as spiral, all the acceleration is in the normal vector, in the normal direction. There is 0 component going into changing the speed. There's no change to the speed. Therefore, AT will always be 0 for any spiral motion. And then the acceleration, the AN would just be the absolute value of the acceleration. So that is our understanding for a spiral motion. See if I omitted any. The section 4 that we have, going through the rest of the homework, let's see. That's different. It looks like a e to the 70 is the magnitude of the motion. Take the spiral. Okay, so you will have to try to find the this is really e to the 70 multiplied by the 70 sine TM1. So you can use product thinking of the as multiplication of 2 vector will make it the calculation derivative easier if that makes sense. And then the derivative will have a separate component of the direction. So work through this. If you have any difficulty, we'll look at it. I don't see any hard part of this because we are not talking about normal vector in this question and the question 2. The next assignment is the part we're going to combine them for. So right now, this one, we are also talking about tangent vector, and therefore I don't see a lot of difficulty with it. And once we move into section 5, we may see some questions like slightly harder. Anyway, in later section of chapter 11 focus a lot on motion. So we can kind of see there's not a lot of additional assignment. And let's try to start section 4. Let me know if you have any difficulty. If not, tomorrow we're probably going to move on to section 5. That should be it today. Thank you. If you can't be late, let me know if you want to record your attendance question.
No problem. That's kind of good. We need to.